Now, here, let's work out a problem. It's a two-dimensional collision. Note that the momentum P is a vector. So, the conservation of the momentum can be expressed into the x direction and y direction for two-dimensional collision. And the key idea here is that the two direction, the momentum conservation along the two directions will be independent with each other. Okay. So if you have two objects collide with each other along one dimension, let's try to write down the momentum conservation for this situation. So if this is for with velocity m1, this is m2. Initial velocity is v1. Final velocity is v2. And after collision, they may move with two different final velocities, say u1 and u2. So here, usually we use v for initial velocity and u for final velocity. Okay. In this case, you can see the initial momentum should equal to the final momentum. But the initial momentum is composed of two terms. This is m1 v1 plus m2 v2. Here v1 v2 can be negative, right? Okay. And this is initial momentum. Final momentum again is composed of two terms, m1 u1 plus m2 u2. So the momentum conservation, if you equal the 2, give you m1 v1 plus m2 v2 equals to m1 u1 plus m2 u2. Okay. So that's a one-dimensional momentum conservation equation. Okay. I guess we don't even have time really to parse that problem. But let's just first look at in general what happens. Now, if you have a two-dimensional collision, so in principle, you should change that scalar equation to a vector equation. So v1, v2, u1, u2 becomes vector. Now we know that how can we deal with vector equation? We just write it along x direction, y direction, or if you have three dimensions, z direction, right? So here, then this becomes two scalar equations. m1 v1x plus m2 v2x equals to m1 u1x plus m2 u2x. This is m1 v1y plus m2 v2y equals to m1 u1y plus m2 u2y. Okay? So for two-dimensional collision, then you have two equations. Of course, that means then you have to, sometimes you need to go through the procedure of vector decomposition. If you know v1, v2, and then you have to decompose it to get v1x, v2x, to put it down in the equation. But this problem, fortunately, you have to decomposition. It's already in the component form. So you already know v1x, v2x, v1y, v2y, right? And then you can find other things. Okay, let's see. We are going to do the problem next class. But once you have the two equations, that's a very simple problem. Okay, I think all of you can just put the number there to get the answer. And here, what I would like to comment is that if we go back to look at the very beginning equation, P naught equals P, if we apply it to one object, okay, if you have only one object, if you don't have collision, so the initial momentum is mv naught. The final momentum is mv. And same object have same mass, so you can see that for one object, the momentum conservation is simply says that object moving with a constant velocity, initial velocity equals to the final, right? Okay, so when you have even one object, you still have the momentum conservation. It just says the velocity wouldn't change without any force. So, okay, so in this way, the momentum model is actually the same as Newton's laws. The momentum conservation is the same as Newton's first law. Okay, think about it, right? Without force, the velocity wouldn't change. The momentum's impulse theorem is equivalent to Newton's second law. Okay, and also if you have two objects, the momentum conservation is actually equivalent to Newton's third law. Okay, you can think about they are the same thing. So for one object, momentum conservation is equivalent to Newton's first law. For two objects, the momentum conservation is equivalent to Newton's third. Okay. So, okay, you can think about that. We are also going to, if we have time, we are going to go back to look at this in detail. I think that's okay. So, no, sorry, we have time. It's just 45. I thought it's already 55. Okay, so now let's look at this in detail. And we can even probably have time to finish it.
Your clock says 9:45? You said 9:45? It's 9:50.
The class should be over at 9:55.
Yeah.
But now it's 45, right?
No, it's 9:50.
9:50, but still have 5 minutes. Okay, please note that it's okay. If I don't finish these things, you still need to look at it, and you have to do it at home. So either way, you still need to take the time. So it's good we use all the time. Possible. Okay, so you can see that for one object, the Newton first law says that if F net equals to 0, V must be a constant, right? And that's exactly the momentum conservation for one object. mv not equals to mv if F net equals to 0, right? And the Newton's second law says that F net equals to ma or m dv over dt. And here impulse momentum theorem says that F net dt equals to m dv, this one, or j equals to delta t, right? So they are the same thing. We simply integrate this with respect to the time. So the third law says that if reaction, if F12 equals to negative F21, the action and reaction. And here, for the two objects, you have M1, V1 equals to plus M2, V2 equals to M1, U1 plus M2, U2. Okay, let's see the equivalence between the two. We can do it this way. Let's put all the M1 on one side. Okay, so you get M1 V1 minus M1 U1 equals to M2 U2 minus M2 V2. Okay, so one object on left hand side, another object on right hand side. Okay? And then we will write it as M1. Okay. Negative M1U2 minus M1. Okay, this is U1. M1U1 minus M1V1. Okay, I want to use final subtract the initial, so I put a negative sign in front of it. This side you get M2U2. This is already final subtract the initial. So this is negative M1U1 minus V1. This is M2U2 minus V2. Okay, this is final velocity, subtract the initial velocity. Final velocity, subtract the initial for the two different poles. So this is negative M1 delta V1. This is delta V2. Okay? The change in the velocity for object 1. Change in the velocity for object 2. And now, that's the equation. So I can try to divide both sides. Time interval. The same collision, they have the same time interval, right? Now you can see what's this and this. This is M1A1, negative M1A1. This is A2, right? Now, by the new definition of the force, okay, not by the definition, by the Newton's second law. So you get negative F1 equals to F2, Newton's third. The force acted on the object 1 and object 2 will be equal but opposite. In fact, in the modern way to establish the mechanics, many physicists prefer to define the velocity first and then the momentum, and then derive this, and then we introduce the force as a definition of M1 multiplied by M1. So in that case, we introduce the force after we have the acceleration. So the force is, we think that that's not something originally or fundamental here. It's simply the acceleration multiplied by the mass. Okay. So in that way, we think about acceleration first, and then we, in Newton's point of view, we think about force first, and say the force introduce or produce the acceleration. But now we think about, we have acceleration, and then we have force. Force is that's something name for this term. Okay, that's related to many modern point of view of the physics. Okay, because in the modern physics, force is not the fundamental stuff. It's derived from other more fundamental things like energy or motion. Okay.